Okay, so hello and welcome back to the weekly live sessions on wheeled mobile robots. I hope my audio visuals are well and good, I suppose. So I'll just give a message if my audio visual is fine enough. I hope it's all right. If there is any issues, please let me know through you can voice your concerns. You can speak up. You can voice your concerns. No worries. So yeah, I will just continue where we have left off from the previous session. So for the week one, during the previous tutorial session, we have basically covered a brief introduction to what this course is all about. Actually, we started with the basic, different sort of systems involved in robotics. Then we narrowed it down to mobile robots, and in mobile robots, we have actually seen there are multiple sort of ways that you can realize locomotion. Be it aerial robots, be it underwater robots, be it mobile robots. Further, we have narrowed it down to wheeled mobile robots. Actually, like apart from mobile robots, there is a distinct category called terrestrial robots or land-based robots. And within the land-based robots, we have even further classifications, right? We have, bipedal walking like robots. We have hopping robots. Then what else do we have? We have wheeled mobile robots. Then we have tracked robots. We have hybrid robots. And then we again furthered it down to wheeled mobile robots. So that is the topic of our course, basically, wheeled mobile robots. So you can see, how we have narrowed it down to all other robotic systems, from manipulators, then mobile robots to terrestrial robots, then from terrestrial robots, we got into wheeled mobile robots. So the topic of this week's sessions are mostly the kinematic modeling of wheeled mobile robots, right? So from this week onwards, we are actually getting on to the mechanics part, which essentially consists of kinematics and dynamics. So for this, we will start our discussions on mechanics, and these are the contents that I have that I would like to discuss for the duration of the next 2 hours. Now we would be discussing a generalized wheel kinematic model, which is basically a generalized kinematic model that you can adapt to use it with different configurations of wheeled mobile robots. And then we'll share some examples, how we can adapt a generalized wheel kinematic model to specific cases. And then we'll see, what is the distinction between a holonomic robot and a non-holonomic robot, and what are their capabilities. So just like what we did with the last session, I intend to, do a bit of a summary of all the topics that we have covered during the lectures. Then on the later part of the lectures, we will solve some practice problems. Right. So we'll begin with the generalized wheel model. So the purpose is that, like, as you might know, if you have seen the lectures, you might have come across different configurations of mobile robot bases, right? What are the typical configurations that you have come across? We have seen this differential drive robots. We have this differential drive robots, and then we have seen, a four-wheel skid steering robot. And then what else we have seen? We have seen a four-wheeled mechanism drive robot. Mechanism drive. Then we have seen a configuration with 3 omni wheels. Then there are even further number of applications, a tricycle-like application. Tricycle-like case. You can have something called a 4 or a 2 swerve drive configuration. And many more such configurations. So the thing is that we need a general model so that we can easily adapt to all of these configurations, right? A differential drive only has 2 wheels, right? 2 wheels on either side of the robot. A 4-wheel skid steering will have 4 wheels. But then again, the principle is still similar to differential wheel drive. You basically locomote the mobile base using different velocities in either of these wheels. And in case of a mechanism wheel and an omni wheel, they'll have these sort of passive rollers on their wheels. If you consider this as a wheel, a typical wheel of a robot, I've already depicted a single wheel. And on these wheels, on the periphery of these wheels, you have these passive rollers throughout its periphery. It could be of different configurations. It's aligned in different angles. And these passive rollers would enable the wheel to slide in a lateral direction, right? As opposed to a conventional wheel. So like if I draw a conventional wheel like this, and if you consider this axis to be the hub of the conventional wheel, it will have infinite resistance along the lateral direction, right? It will have a huge, mathematically, if you're modeling, you will model the conventional wheel to have infinite resistance along the lateral direction. So it cannot slide like this. But in case of an unconventional wheel, as we use in this mechanism wheel and omni wheel drives, we have this small passive rollers throughout the periphery of these wheels. So these wheels, their axis is like this. It's orthogonal to the main hub axis. So these passive rollers would enable a wheel to have capability to slide in the lateral direction, right? It won't offer any sort of resistance. So these sort of wheels would give a mobile robot an even higher degree of maneuverability, right? So that it does it can basically move in a lateral direction without changing its orientation. So for all these purposes, in order for us to adapt the kinematic model to all of these cases, we would need a generalized wheel kinematic model so that we can find a relationship between the angular velocity of the wheel to the velocities of the mobile robot chassis. So in the previous case, in the previous lecture, we have come across a relation, the kinematic relation, that is eta dot as j of psi multiplied by theta, right? Where this eta dot is the velocity of the mobile robot uh, in the world fixed frame, or in the inertial frame of reference. So this eta dot is nothing but x dot, y dot, and psi dot, where x dot is the velocity, is the linear velocity along the inertial x-axis of the inertial frame of reference. Y dot is the velocity, linear velocity along the inertial uh, y-axis, and psi dot is basically the angular rotation rate about the inertial z-axis. And the psi is nothing but uh, the velocities in the frame of reference that is attached to the chassis of the robot. That is nothing but UVR, where U is the linear velocity along this xb axis, and V is the linear velocity along the yb axis, and R is the angular velocity along the zb axis. And the reason for this mapping is that we give the control with respect to the theta frame, right? Because the motors, all the actuators are located on the mobile robot, and we give the commands with respect to this zeta axis. But the reason why that we are using this mapping, from zeta to eta, is because we basically visualize, or we can only observe the robot with respect to this inertial frame of reference, right? Because as an observer, located we would be located on the ground. We won't be so we have nothing to do with this body fixed frame, because our frame of reference will always be with respect to this inertial frame of reference. And in order for us to observe the robot, or to intuitively visualize what the robot is basically doing, we need to have this sort of a mapping. But as you can see, this mapping is a very, general mapping. It does not have anything to do with, what sort of wheel a robot has, or how many number of wheels a robot has, or whether it has passive rollers or whether it is a conventional wheel, the number of wheels that are involved. This has nothing to do with the wheel configuration, right? Because it is applicable to any of the robot configuration. But we are interested to find one more step, right? So in this class, we find a relation that we can map this theta to the angular velocity of the wheel using a wheel mapping matrix, or a wheel characteristic matrix. We call this as this W matrix, right? Our objective for this class is to find out what this W matrix is, so that we can actually create a mapping from zeta coordinate to the wheel's angular velocity. Because this is what our input would be, right? The angular velocity of each of these wheels would be given as an input to the actuators. So this would make it more specific. This sort of mapping would be more specific depending on the configuration that you would be using, right? And so for that, to have a W matrix, or to have this assembly matrix, we need to find a generalized wheel model. So we'll basically, look into the derivation of that in a detailed manner. So before we begin, I'll just explain on what I currently have on this board. We have this inertial frame of reference that is fixed to the ground. We have this frame of reference that is attached to the body. We call this frame B. So this frame basically moves with the body. And you can consider this angle of orientation between the body fixed frame of reference with respect to the inertial frame of reference. You can consider it to be psi. This angle psi, right? Okay, so now moving on, we also have one more frame of reference. We call this XCI, YCI. We call this frame of reference as CI. CI, if I label this as CI. So what this axis corresponds to, this CI frame of reference corresponds to the steering coordinate frame, right? So depending on the steering angle, the angle, the relative orientation between XB and XC basically changes, right? If there is no steering angle, the wheel would be oriented like this. If there is some steering angle, it would be oriented like this, right? And the steering angle, depending on the steering angle, the wheel's orientation can change. So we would represent the steering angle using this parameter. I am writing it here. I write this relative orientation between XCI and XBI as theta BI, right? Where I is the wheel that we are considering, right? If there are only two wheels, I would be one and two. If there are four wheels, I would be one, two, three, four. So in this case, we are basically considering this particular wheel, right? So theta BI is nothing but the steering angle between the steering angle. It's a parameter used to represent the steering angle. And then we need one more parameter to define this the orientation of this passive roller. So I'll use one parameter. I'll call this as phi I. Phi I. So this is nothing but the angle, the the sliding velocity of the passive roller makes with the YCI axis. We can fix it based on the convention that we are following in this course. So this angle, whatever this passive roller makes with this YCI axis, we call this as phi I. So what are the things we have? We have defined this inertial frame of reference, and then we have the body frame of reference. And then we have also defined one more frame, that is CI. This is the frame of reference, or we can call it as wheel frame to represent this the relative steering angle. So how do we define the kinematic? So I'll define a few more terms. We have this term called AI. This is nothing but the radius of the wheel. I'll call this as wheel radius, right? If you consider this as the wheel, the view that you are currently looking at is actually the top view of the mobile robot. This is how the chassis would look like from the top, and this is how the wheel would look like from the top. And I hope this is visible enough. AI is nothing but the wheel radius. And I would define the angular velocity of the wheel as omega I. Well, angular velocity of the ith wheel. So this is the wheel angular velocity. And I would also mention two more parameters. The first thing is rho I. This is nothing but the radius of this passive wheels. Rho I. So that is the passive roller radius. And beta I dot is the angular velocity of the passive roller. So basically, we have defined four terms: the angular velocity, the radius of the wheel, the angular velocity of the wheel, the radius of the passive roller, and the angular velocity of the passive roller. So now what do we do? So if you give an input, or if you give an angular velocity to the wheel using a motor, because each of these wheels are connected to a motor which is attached to its hub. So if you consider these to be the wheel hubs, these wheel hubs would be connected to a motor. So if you are driving this wheel using a motor, the wheels will roll along this XCI direction. right? The wheels will have an angular velocity along this XCI direction. So I'll denote that velocity as the drive velocity, V drive. So what is that V drive? So this V drive is nothing but R omega, right? Or A omega. We'll write this as A omega I AI. So we have one more component, V slide. That is nothing but the linear velocity that is experienced by the periphery of this passive roller. So it will be along this direction, right? It will be along the direction of the passive wheel. So I'll denote that as V slide. So this velocity along the longitudinal direction of the passive wheel, I'll denote it as V slide. So this V slide is nothing but beta I dot multiplied by rho I. Right? Now that we have this V drive and V slide, you can resolve this V drive and V slide along this local frame of reference, YCI and XCI. So how do you do that? So the velocity along this XCI dot, how do you write that? Velocity along this XCI dot, this is nothing but V drive, because V drive is already along that XVI velocity. Then we have a component of this V slide along this line of action. So that component would be minus V slide sine phi I. I hope that is clear. And the Y component, the component along YCI is nothing but YCI dot is nothing but V slide cos phi I. So if I substitute these values into this general equation, what will I get? I'll get the equation of this form, omega I AI minus rho I beta I dot sine phi I. I label this as equation 1. And the second equation could be rho I beta I dot cos phi I. Label this as equation 2. Okay, so in our modeling, we really don't care about this rho I beta I dot because it's not an important factor, right? So our objective is to find out this relation, zeta as a matrix, a transformation matrix multiplied by omega, right? And so far we have, where the zeta is defined, right? The zeta is defined with respect to xb and yb. But we have just begun. So we got something, we can relate omega to this XCI and YCI coordinate. And then we'll somehow work our way to, get all the way back to this YBI and YB and XB frame of reference. So far we are only, we have only related omega I to XCI and YCI. Okay, so now how do you eliminate, how can you eliminate this rho I beta I dot from these two equations? So from equation 2, I can write it as rho I beta I dot as YCI dot divided by cos phi I. So I'll write this as equation 3. And if I substitute this rho I beta I from equation 3 to equation 1, what will you get? So I'll write equation 3 in equation 1. You can write it as XCI dot as omega I AI minus YCI dot by cos phi I sine phi I. So I'll write this as equation 4, right? I hope I'm clear so far. So I'll just rewrite. I can, sorry, I can maybe rewrite this uh, in an vector and matrix form, right? So I'll bring this xci and yci terms on to one side, and I'll keep this omega I to another side. So it's just a matter of rewriting. So I'll do this as follows. So this would imply xci dot plus yci. So this sine phi and cos phi, you can write it as tan phi I. This is nothing but omega I ai. So I can represent this as a vector and matrix form. Omega I as 1 by ai tan phi I by ai multiplied by xci dot yci dot. Right? I'll just put this in a box. I'll call this equation probably 5. Right? Because if you expand this matrix, you will get the previous relationship, right? And you can basically write a similar equation for depending on the configuration of your robot. If you have two wheels, you can have equation 1 as omega 1 is so and so. If you have two wheels, you'll have to write this twice. Okay, so now how would you further expand from this? Now, basically, you have actually obtained a relationship, omega I with respect to this frame of reference, xci and yci. And as you can see, this values xci and xci dot and yci dot, they are represented with respect to the frame of reference ci, this frame of reference. So just to give more clarity, I'll have the suffixes ci and ci. So these superscripts are used to make it more clear that these terms xci dot and yci dot, they are basically represented with respect to the ci frame of reference. And the next step is to represent this xci dot and yci dot with respect to this b frame of reference. So how do you do that? So if you can recall from the previous week, if you have two frame of references like this with a relative orientation, so I'll call this as the B frame, XB, and this could be YB. And you have another frame of reference, which I would mark it. So if this is XCI and if this is YCI, sorry. And the orientation of both of these frames is, the relative orientation is nothing but theta bi. Just like what we have over here, the relative orientation between this xb and yb and xci and yci is theta bi. So if you have this two frame of reference, if you want to transpose the quantities in this ci frame to b frame, you have to use this rotation matrix, right? So in essence, this xci and yci dots with respect to b is nothing but cos theta bi minus sine theta bi, then 0 sine theta bi, cos theta bi, 0, then 0, 0, 1. This rotation matrix multiplied by xci dot yci dot with respect to this ci frame of reference. So where are we? We are in equation 5. I'll call this as equation 6, right? So yeah, now that we can find a transformation from of xci dot and yci dot from ci frame with respect to bi frame, you can substitute this entire relation onto the previous equation 5, right? Or rather, here in this equation, it is referred with respect to xci dot. So to find out this with respect to ci, you have to, you have to take the inverse of this matrix and pre-multiply to the left-hand side. So I'll rewrite it again. So how do you write this? xci dot yci dot with respect to this ci frame of reference is nothing but the inverse of this rotation matrix. This is a rotation matrix. So what would be the inverse of this rotation matrix? It would be its transpose, right? Because this is an orthonormal matrix. So the inverse of an orthonormal matrix is just its transpose. So if I take the transpose of this rotation matrix, it will look like cos theta bi, sin theta bi. Then we have, sorry, I think it does not have to be a 3 by 3 matrix. It only need to be a 2 by 2 matrix, like so. Sorry if I have confused, because this is a 2 cross 2 matrix, as this is a 2 cross 1 vector. This is also 2 cross 1 vector. So taking the transpose of this matrix, it would look like cos theta bi, sin theta bi. Then we have minus sin theta bi, cos theta bi. This, we pre-multiply this with the left-hand side. So that makes it xci dot with respect to b, yci dot with respect to b. So I'll call this as equation 7. And if I substitute equation 7 into equation 5, the equation that we have highlighted over here, we would end up as omega I is 1 by ai and phi I by ai. Then we have, instead of this term, we would substitute this entire matrix vector equation. So we get cos theta bi, sin theta bi, minus sin theta bi, cos theta bi, multiplied by xci dot yci dot with respect to the b body fixed frame of reference. So I label this as equation 8. So we have reached thus far, right? So as a summary, we have earlier defined, we have initially found out a mapping between omega I and xci dot. And now we have found out a mapping between omega I and this B with respect to this B frame of reference, right? So omega I with respect to the B frame of reference. Now, again, looking back to the body, what exactly is this? What exactly is, sorry, what exactly are these terms xci dot and yci dot with respect to B frame of reference? You can write it in terms of UVR. You can write this xci dot uh, and yci dot as a function of UVR. That is nothing but the velocity along xb axis, velocity along yb axis, and velocity, angular velocity along the zb axis. So what you do is that you have, if you consider the the position vector of the Ci with respect to Bi, I'll label this position vectors. If I call this distance as dyi, the vertical distance, and if I label this horizontal distance as dxi, right? So the position vector of this Ci frame with respect to B frame is dx in the x direction and dy in the y direction. So the velocity of this point C would be r cross f, right? If you write it in vector form, the velocity of the point Ci with respect to V would be r cross the position vector cross the angular velocity, or angular velocity cross that position vector. So how would that look like? So I'll write one more equation. So this Vxci, sorry, xci dot with respect to B and yci dot with respect to B. The first equation is nothing but u minus r dyi, and the second equation is v plus r dxi. I hope it is clear enough. So I label this as equation 9 and I'll label this as equation 10. Right? And the way we got this is basically we have this position vectors dxi along this I unit vector and dyi along the j unit vector. So we do this omega cross r, the linear velocity equation. One second, I'll just we do this rk. So this term is the angular velocity of the robot along the B frame of reference, and this is the position vector of the Ci frame with respect to the B frame or the body rigid frame of reference. So if you expand this cross product, what will you get? If you expand that, you will get r dxi, and k cross I is nothing but j plus r dyi. K cross j is minus I. So this becomes minus I. Right? So the two components are minus r dyi and r dxi. But you will have to add this with the u component and v component. The reason is that the mobile robot will have a velocity along xb axis and yb axis as u and v. So you will have to superimpose that u and v onto this expression, whatever we have obtained from omega cross r. Right? So I can write this in a vector and matrix form like so. So I'll write this in the vector and matrix form. Xci dot the yci dot. This I can relate this to UVR using this following transformation matrix. 1, 0 minus dyi, 0, 1 dxi. So I'll call this equation 11. Right? And if I substitute, this equation 11, onto equation 8, right? In place of this, in place of this vector, I would substitute in place of this vector, whatever we have obtained on the right-hand side of equation 11. So in effect, we will get this final lengthy transformation matrix, that essentially maps the wheel angular velocity to the velocity coordinates of the body frame of reference. So this is basically the generalized wheel model, that basically maps the angular velocity of the wheel to the velocity coordinates of the body fixed frame of reference. So we can basically do one thing. We have basically plenty of use cases, like what we have defined using this figure. So this is nothing but a differential wheel drive. It's a very simple configuration. It only has two wheels, two driven wheels, right? So I'll label this as the first wheel and this to be the second wheel. So the typical convention is that we'll consider this axis along XB as the longitudinal, and the direction along the YB axis as the lateral direction. And another convention that we are following is that we will consider the side along the positive YB axis as the left side, and the side that is aligned on the negative YB axis as the right side, So how can you apply the generalized wheel model in case of a differential wheel robot? So let me see if I can just take a screenshot of this. Uh, yeah. Copy. And if I can replicate it over here, if I paste it over here. So how can you adapt this generalized wheel model to a differential wheel robot? So the first thing we can do is that we count the number of wheels, and the number of wheels is 2 basically. So I over here is going to be 2. So we'll consider the wheels one by one. So for the first wheel, what are these parameters? So AI or A1 is nothing but the wheel radius. So we'll consider the wheel radius to be constant, obviously, because for a differential wheel robot, the wheel radius is basically constant for all the wheels. So AI, or when A is 1, is considered A, the wheel radius A, whatever be the case. And what was phi I? Phi I was the angle that a passive roller would make with respect to the YCI axis. YCI is the y coordinate of the steering axis. So in this case, since we don't have any passive rollers, it's just a conventional wheel. The phi 1 or phi 1 is basically 0. And then what are the other parameters? We have this theta bi. So theta b1 is also going to be 0 because the wheels also does not have any steering capabilities. The orientation of the wheels are fixed at all times. Then what are this dyi and dxi? So dyi is nothing but the distance from the body frame of reference. If I call this as the body frame of reference to the wheel frame of reference. So essentially we have a wheel frame of reference like so. I'll call this as XCI. Sorry, this is to be YCI and this is to be XCI. So dyi is the y component of the unit vector from B frame to the CI frame. So since if you consider the width of the robot to be 2D, like so, the distance from the B frame to the first wheel is nothing but D in the positive y-axis plus D. And what is this other term, dxi? Dxi is going to be 0, right? Because there is no x component because they are aligned along a vertical line. So the x component is 0. So if you substitute all of these values onto this generalized wheel model, you will be basically getting as omega 1 as 1 by a, tan phi 0. So this will be 0. Then what are the other terms? This multiplied by cos 0, sine 0, minus sine 0. This will be cos 0. Then you will have 1, 0 minus d, 0, 1, 0. Then you multiply this by UVR. So if you simplify this out, if you expand this equation out, you will get something as follows: omega 1 as 1 by a, 0 minus d by a multiplied by UVR. Right? So I'll just label it like so. And using a similar method, you can consider you can have a mapping from omega 2, right? The angular velocity of the second wheel to UVR, right? UVR basically that is the velocity, linear velocity along XB axis, linear velocity along YB axis, and the rotation along ZB axis. So if you consider the parameters, A2 for the second wheel would be A, same radius. Phi 2 is again 0. Theta B2 is again 0. DYI in this instance is basically the distance from frame B to the second frame of reference. So if I call the wheel frame of reference of the second wheel as this to be X B2 and this to be Y B2. So this distance dy2 is actually minus d because it is oriented in the negative y-axis or negative yb axis. So dy2 here, dy2 would be negative d, and same as before, dx2 is 0. So if you substitute all of these parameters into this generalized wheel model, the final expression would look something like this. Omega 2 is 1 by a, 0, then you will get a plus d by a, this multiplied by UVR. Right? And you can basically combine these two equations into a very compact matrix and vector form like so. So if I combine these two equations, omega 1, omega 2 would look something like this. It'll be 1 by a, 0 minus d by a. And the second row would be 1 by a, 0 d by a, this multiplied by UVR. Right? This expression. So the meaning of this is that if you know the wheel velocity, if you want to give some inputs to this differential wheel robot, so if you give some values to this omega 1 and omega 2, based on this parameters, based on the dimensions of these values d and a, you can actually see what are the values of u, v, and r. Right? So in order for to do that, if you know this vector, you have to take this matrix, take its inverse and pre-multiply it in order for you to find this u, v, and r. Or if you want to find the other way around, if you know this u, v, and r, if you want to specify the robot to move in a specific direction that is defined by this u, v, r, and if you want to compute this omega 1 and omega 2, you can simply pre-multiply these two quantities. either ways, the forward problem or the inverse problem, you can basically find out using this relationship. And the general form that I would like to bring to your attention would look something like this. So again, if you take a look at this matrix, this is a non-square matrix, right? So it has 3 columns and 2 rows. And if you want to take the inverse of a non-square matrix, you will have to use something called a pseudo-inverse, pseudo-inverse. So we will look at the pseudo-inverse uh, a bit later into this lectures, but for the time being, you know that you know how to take the pseudo-inverse. So how can you write, if you take the pseudo-inverse and pre-multiply into this left-hand side, you will get the following relation as UVR as a by 2, 0, 0, minus a by 2d, this whole thing multiplied by omega 1 and omega 2. Where this matrix is basically the pseudo inverse of this matrix. So if I highlight this over here, this is actually a mapping between omega 1 and omega 2, the wheel angular velocity to UVR, the velocity coordinates in the body fixed frame of reference. And we call this matrix, as the wheel configuration matrix of a differential drive robot. So this can be written in a compact form as zeta as W multiplied by the angular velocity vector, where zeta is UVR, the vector of UVR, and this omega vector is the vector of angular velocities, omega 1 and omega 2, and this W is this wheel configuration matrix, which basically depends on the configuration of the mobile robot that you are analyzing. Okay, so on a similar fashion, we will see one more example. So in this case, this is a skid steering robot. We have all 4 wheels. We have 4 wheels. Actually, this is wheel 1, this is wheel 2, this is wheel 3, this is wheel 4. So if you give equal angular velocities for all the 4 wheels in equal direction or in the same direction, this mobile robot would go in this direction. And if you reverse the direction, if the velocity is along this direction, equal angular velocities for all the 4 wheels, the robot would go in this direction. And what happens in this case, if angular velocity of wheel 1 is in this sense, and angular velocity of wheel 2 is in this sense, and angular velocity of wheel 3 is in the opposite sense, and same with wheel 4. So if this is how you give the angular velocities, wheel 1 and wheel 2 move forward and wheel 3 and wheel 4 move backward, this entire robot would rotate like this about its own axis, with 0 turning radius. It would just execute a rotation like this. And similar thing, if you invert the direction, just like what we have seen earlier, what will it happen? It will again rotate about its vertical axis in the counterclockwise direction. And another thing is that if you have a small angular velocity like this for wheels 1 and 2, and if you have a larger angular velocity for wheels 3 and 4, but all the angular velocities are in the same direction, so the robot would move something like this. It will take a curve. It will take a curve in the counterclockwise sense, but with the finite turning radius, with a larger turning radius. And same thing happens, if you have a larger velocities along the left side, but smaller velocities on the right side, it will take a curve-like trajectory, but the curve would be, it will be curving in the clockwise direction. in the clockwise direction. But again, with a larger turning radius, with a finite turning radius. So these are the possible movements these sort of robots will have. So if I reproduce the wheel configuration matrix like so, we have four wheels. So like we'll have to evaluate this omega I four different times for four cases. So AI or A1, when I is 1, so yeah. So here, this is wheel 1, this is wheel 2, this is wheel 3, and this is wheel 4. So when I is 1, A1 is A, phi 1 is 0, theta B1 is 0, dy1 is, if you consider this distance to be d, that is half of 2d, d1 would be d, dy1 would be d, and dx1 would be. So if this distance is 2l, this distance is L, going to be L. And when I is 2, A1 is A, phi 2 is again 0, theta B2 is 0, dy2 is D, but dx2 is minus L. And when I is 3, A3 is A, phi 2 is 0, theta B2 is 0, dy2 is minus D, and these are all 3's, right? And dx3 is minus L. And when I is equal to 4, A4 is A, phi 4 is 0, theta B4 is 0, dy4 is minus D, and dx4 is L. So if you substitute all of these individual cases into this generalized wheel model, you would be basically getting the following equations, which are omega 1 as 1 by A, 0 minus D by A, multiplied by UVR. Omega 2 is nothing but 1 by A, 0 minus D by A, UVR. Omega 3 is nothing but 1 by A, 0 D by A, UVR. And omega 4 is nothing but 1 by A, 0 D by A, UVR. And if you club all of this together into a single matrix and vector form, you will have something like this. Omega, I'll write it like this. You will get a big matrix, omega 1, omega 2, omega 3, omega 4 as 1 by A, 0 minus D by A, 1 by A, 0 minus D by A, 1 by A, 0 D by A, and 1 by A, 0 D by A. This whole matrix would be multiplied by UVR, where this vector is omega, and this vector is zeta, and this matrix is basically the pseudo inverse of this wheel configuration matrix. But the general format is to write it as zeta as W multiplied by omega. So to bring this equation into this form, you have to take the pseudo inverse of this matrix and pre-multiply it with this omega vector. So if you do that, at the end, you will get this final expression as UVR as A by 4 multiplied by 1, 1, 1, 1, 0, 0, 0, 0, minus 1 by D, minus 1 by D, 1 by D, 1 by D. this multiplied by omega 1, omega 2, omega 3, omega 4. So as you can see, if you can notice, the entire second row is basically zeros, right? So no matter whatever combination of omega 1, omega 2, omega 3, omega 4 you have, this component, the V component is always going to be zero. And the reason is that these are all unconventional wheels. These are all conventional wheels, and they provide infinite resistance along the lateral direction. So, whatever combinations that you use for omega 1 to 4, this robot cannot slide. This robot cannot move along the YB direction, right? It can go forward, it can go backward, it can rotate about its own axis, with zero turning radius, or it can take, it can take a curve with a finite turning radius. All these motions are possible, but it cannot simply go lateral, by keeping its orientation, it cannot go in the lateral direction because these wheels are conventional. So that's why we ended up with, the second row being all zeros. And another case is this, what we call this as a mechanical wheel drive. And again, if you reproduce this wheel configuration matrix, you will have to evaluate this 4 times. But in this case, this becomes a bit more involved because as you can see, you have this passive rollers. And like basically these are aligned 45 degrees with respect to the steering, with respect to the wheel frame of reference. This case, this is plus 45 degrees. And in this case, it is minus 45 degrees. And in this case, it is plus 45 degrees. And in this case, it is minus 45 degrees. As you can see, the diagonal wheels are aligned similarly in a similar sense, right? So in this case, this phi I is no longer zero, right? So depending on the wheel, it could be plus 45 or minus 45. Theta bi remains zero, right? Because it does not have any independent steering control. So xci and yci are always going to be oriented similar to xb and yb. There is no relative orientation between xci and yci. So the relative orientation is always going to be zero. And taking that into consideration, AI, or in case of all the 4 wheels, A1, A2, A3, A4, they're all going to be the same, which is A. And phi I for wheel 1 is going to be 45 degrees. And for wheel 2, it's going to be minus 45 degrees. And for wheel 3, this is going to be plus 45 degrees. And wheel 4, it is going to be minus 45 degrees. And theta B1, theta B2, theta B3, and theta B4, they're all going to be zero. Because the wheel frame of reference is oriented. There is no relative orientation between the wheel frame of reference and the body frame of reference. And the remaining parameter dyi and dxi is similar to what we have just seen. If you consider this to be 2D and if you consider this to be 2L, the unit vector or the components of the vector along xb and yb for each of these points, each of the for each of the centers of these wheel frame of reference is exactly how we figured out in the previous case. Okay, so in this case, if you want to write this equation, zeta as a wheel configuration matrix multiplied by W, where zeta is nothing but this UVR, and omega is nothing but omega 1, omega 2, omega 3, omega 4. The angular velocities of these individual wheels, your W matrix would end up looking something like this. This will be A by 4. If you do the derivation, it will be like 1, 1, 1, 1, 1 minus 1, 1 minus 1, minus 1 by d minus L minus 1 by d minus L, 1 by d minus L, 1 by d minus L, right? So unlike the previous case, we don't have any rows with full zeros. All the elements are fully populated. So that basically gives this robot a very high degree of maneuverability, right? It can move in the forward direction, it can move in the backward direction. It can rotate about its own axis with zero turning radius. It can take a curve like this or like this with finite turning radius. Apart from that, it can go like this, it can go in the lateral direction, by keeping its orientation constant, it can simply slide, left and right, just like that. It can also move diagonally like this, right? Just by keeping its orientation, at one instant it would be like this. At the next instant, it would be like this. At the next instant, it would be like this. But all these cases, the orientation is actually the same. So, but it can, slide in the diagonal direction. And it can also move in the lateral direction like this. One instant it would be like this. Another instant it would be like this, by keeping its orientation constant. So the model for mechanical wheel drive has much more higher degree of maneuverability as compared with the previous two cases, the skid steering and the differential wheel drive. One more case that I would like to bring to your attention. We have seen this before. Another case is this omni-wheel drive. So here we have three wheels like so, and the three wheels have passive rollers on the periphery of these three wheels. And each of these three wheels are aligned, and their hubs are actually aligned 120 degrees apart. Again, if you reproduce this wheel configuration matrix, you will have to do this 3 times because there are three wheels. So what are these components? Phi I. So phi 1 would be, I may have probably made a small mistake. The XCI axis would be like this. It should be aligned along the longitudinal direction of the wheel, like so. So I'll probably redraw this with red color. So this is supposed to be XC1, and this is supposed to be YC1. So I'll just scratch this out. Because by convention, XC1 is aligned with respect to the wheel's longitudinal axis, right? If you go back to the derivation, XC1 is actually aligned with respect to the longitudinal direction of the wheel, and YC1 is aligned with respect to the hub of the wheel or perpendicular to XC1. So in this sense, what is phi 1? So if you can recall, phi 1 is basically the angle that these passive rollers makes with respect to the YCI axis, right? But in this case, the passive rollers are aligned with respect to YC1. Their relative orientation is basically 0. They are aligned. So phi 1 is going to be 0. And it's actually the same for all the frames. So phi 1, phi 2, and phi 3, they're all going to be 0. Right? Because if you want to take another example, XC2 would be something like this. Along the longitudinal direction of the second wheel. This is, XC2, and YC2 would be something like this. This is YC2, And in case of the second wheel, over here, again, the passive roller here is aligned with respect to the YC2 axis. So that makes phi 2 0, and similar can be set for phi 3 as well. Phi 3 is also 0. All right, then what are the terms? We have established that phi I is 0. Then the radius of the wheel, A1, A2, A3 are all constant. We'll call this as A. And then what about theta B? Theta B1, theta B2, theta B3. So if you can recall, theta B is basically the relative orientation between the wheel frame of reference with respect to the body frame of reference. Right? So this is the body frame of reference, YB and XB. And this is the wheel frame of reference, XC1 and YC1. But as you can see, XC1 is 90 degrees oriented with respect to XB, and YC1 is also oriented at a 90-degree orientation. Right? YC1 is oriented 90 degrees with respect to YB, and XC1 is oriented 90 degrees with respect to XB. So that we can actually say this as 90 degrees. Theta B1 would be 90 degrees. And what about the second wheel? You basically know that all the three wheels are oriented 120 degrees apart. Right? This wheel is the second wheel is oriented 120 degrees with respect to the first wheel, and the third wheel is oriented 120 degrees with respect to the second wheel, and 240 degrees with respect to the first wheel. So YC1 is already has already got a 90 degrees head start with respect to XB and YB. Then what about the relative orientation between XC2 and YC2 with respect to XB and YB? That will be 90 degrees plus 120. That is nothing but 210. And theta B3 would be, it will be 90 degrees plus 240. That is nothing but 330. Right? So theta B1 is 90 degrees, theta B2 is 210 degrees, and theta B3 is 330 degrees. And what about dx1, dy1, dx2, dy2, dx3, dy3? What about these coordinates? So if you consider the radial distance from B frame to the C1 frame as L, same goes for the radial distance between B frame and C2 frame, L. Same goes for B frame and C3 frame as L. So x1 is basically the x coordinate of the position vector from B frame to C1 frame, that is L, and dy1 would be 0. Then what about dx2? So if this angle is 120 degrees, dx2 would be cos 120, dy2 would be sine 120. And between 3 and B, this angle is basically 240. Right? So dx3 is, this is L cos 120, this is L sine 120. And this becomes L cos 240, this becomes L sine 240. So if you plug all these values into this generalized wheel model, ultimately you will derive this wheel configuration matrix as follows: 0 minus a root 3 by 3, a root 3 by 3, then we have 2a by 3, minus a by 3, minus a by 3, then you have this a by 3l, a by 3l, a by 3l. All right. So again, as you can see, none of you don't, at least there is one non-zero element in all of these rows. So just like in that mechanism wheel, this robot, this configuration can also move in wide variety of ways. It can move in the forward direction. It can move in the backward direction. It can rotate with zero turning radius. It can rotate with the finite turning radius. It can move in the lateral direction. It can move diagonally. All sort of maneuverability is possible using this configuration. Even for a mechanism wheel. Yeah. So yeah, that's about it. And with that, you can basically get into some problem solving, unless you have any doubts that you would like to get clarified. Shall we move on to some problem solving? Or is there any topic that you would like to have more clarity from the lectures? Any responses? Okay, so in the lectures, we have also considered a case. We just now we have derived this expression, theta as W multiplied by omega, where this theta is nothing but UVR, and this omega is nothing but omega 1, omega 2, etc., depending on the number of wheels. And this W is basically the wheel configuration matrix. So the thing is that the shape of this W matrix, it can change with respect to the configuration that you are dealing with. But it's most in most cases it's not going to be a square matrix. You know the order of this W matrix can be written as W m by n or m cross n, and you may end up with several situations where in some situations this m would be greater than n, and in some other situations m would be less than n, right? And you may also end up in some situations where you will have to invert this matrix. Sometimes you are given zeta, you are required to find omega. So what happens is that you will have to invert this matrix and bring it over to this left hand side to find this unknown omega. So depending on if you have a matrix that has m greater than n, or if you have m less than n, you will have to take something called a pseudo inverse, right? Because if the W matrix is not square, you will have to take you will have to take the pseudo inverse rather than a regular inverse, because a regular inverse is defined only for a square matrix. So in this case, when m is greater than n, you can take the left pseudo inverse, and when m is less than n, you will have to take the right pseudo inverse. And the expression for this left pseudo inverse is nothing but uh, W transpose W, the whole inverse, W transpose. And the right pseudo inverse is W transpose, the whole inverse, W transpose. Right? And in the lectures, we have seen how to derive these expressions, how to derive this expression for the left pseudo inverse and the right pseudo inverse. We derive the left pseudo inverse by using the least square approach. And you derive this right pseudo inverse using the minimal norm approach. I don't think we have enough time to discuss the derivations of either of these two cases, the left pseudo inverse and the right pseudo inverse. And why are we going with this least squares approach for a left pseudo inverse, and why are we going for a right pseudo inverse for why are we going for this minimal norm approach for the right pseudo inverse? In strict linear algebra terms, it has its own meanings, or it has its own implications. But I would recommend you to go through the lectures uh, if you are more interested to see, how we are deriving this pseudo inverse matrices. Uh, or if you have any more doubts, or if you want more clarity, you can always get back to me through the discussion forums. It's not really practical for us to discuss that during this session because we only have a limited amount of time. Okay, so with that, we shall move on to solving a few sample questions. Okay, so the first question basically says, in a two fixed wheel differential drive mobile robot, the left side wheel angular velocity is 0.5 radians per second, and the right side wheel angular velocity is 1.5 radians per second. So if you consider this to be the differential wheel robot, we have the body fixed frame of reference like so. This is YB, this is XB, and we have two wheels, one at the left-hand side and one at the right-hand side, right? So as per our convention, the side that is aligned with respect to the positive y-axis, we call this as left, and the other side is right. And as per the question, it has been given that the left hand side wheel angular has a angular velocity of omega 1 as 0.5 radians per second. And the right hand side wheel has an angular velocity of 1.5 omega 2 as 1.5 radians per second. You are also given the wheel radius A1 and A2 as 10 centimeters in the question. Here it is, the wheel radius is 10 centimeters. You are asked to find out what will be the longitudinal velocity of the robot with respect to the body frame of reference. So this is the body frame of reference, this XB and YB frame coordinate. And you are asked to find out the velocity, longitudinal velocity, that is the velocity along this XB axis, U. This is what you are asked to find out, right? So either you can do this in a geometrical way because, if you consider this to be the center of wheel one, the velocity, if you consider the velocity v1 as omega 1 times a1, this is nothing but 0.5 multiplied by 10 centimeters. If you convert that into meters, it will be 0.1. So, or if you consider it is in centimeters itself, it will be like 5 centimeters per second. And on the right hand side, you have a larger velocity v2. This is nothing but omega 2 multiplied by a2. This is 1.5 multiplied by 10. This is nothing but 15 centimeters per second. This is, so you can basically consider this to be a trapezium, where one side has the length v1, the other side has a length v2. You are required to find out the velocity, the longitudinal velocity of the wheel with respect to the body frame of reference. So if you consider this line, connecting the centers of the two wheel, the body fixed frame of reference is attached at the middle here, right? So here is your body fixed frame of reference B. You're asked to find out the longitudinal velocity u of the body fixed frame of reference. So in a trapezium, if you know the length of the two parallel sides, the height of the trapezium from its midpoint is nothing but the average of these two sides. So u is nothing but the average of v1 and v2. So that is, what would that be? That is going to be 10 centimeters per second, or it's going to be, I believe, 1, right? Sorry, 10, but it's going to be 0.1 meters per second. I suppose that is all right. Or this is one method, or you can go back to the case of that wheel configuration matrix of a differential wheel drive. As you can see, that the wheel configuration matrix of a differential wheel drive is given by this matrix. So I'll just copy this. If I copy this and if I paste it over here, we'll go with the traditional way. So I'll just erase these unwanted bits. So this over here, this over here is this wheel configuration matrix of a differential wheel drive. And you can post multiply this with omega 1 and omega 2. This would give you UVR, right? Because this is that well-known relation that we have just derived. This is the theta vector, this is the W vector, and this is the omega vector, right? So all these parameters are given, all these parameters are given, and the wheel angular velocities are also given, right? So UVR is nothing but A is given as, how much is A? It's given as 10 centimeters. So A by 2 is 5 centimeters, 5 centimeters. The second row is going to be 0. And the third row is 10 by 2 multiplied by D. It's irrelevant. D is basically irrelevant in this case. A by 2D, it's minus A by 2D and plus A by 2D. And we multiply this with the wheel angular velocities, that is 0.5 and 10. Sorry, it's 1.5. So if you multiply this out, at least you can try and multiply this out, the first elements, actually, the first row and the columns, because you are only required to find out this first term. So if you multiply this out, you would end up as, u would be 5 multiplied by 0.5 plus 5 multiplied by 1.5. So this is nothing but 2.5 plus 7.5. You will end up with, again, 10 centimeters per second. This is nothing but 0.1 meters per second. You will again end up with the same answer, right? So in that regard, the correct answer in this case is 0.1 meters per second. Let's check the answer. So that is indeed correct. So let me know if you find it, if you need more clarity into this, right? Because we know this theta as W multiplied by omega. We are required to find out one component of this theta vector. You are given enough details to populate this W matrix, and you are also given the elements of this omega vector. Right? These are actually vectors. So the only thing you have to do is you multiply the constituent elements of this vector and matrix, or this matrix and vector, and simply equate the relevant entries from left hand side and right hand side. Okay, so moving on to second question, question 2. It's again a question on differential wheel robot. So in a two-wheel differential wheel robot, the left-hand side wheel angular velocity is given as 1.5. So omega 1 is given as 1.5. And the second right-hand side wheel angular velocity is given as 0.5. The units are radians per second. What else do we have? Both wheels are of the same size and the wheel radius is 10 centimeters. So A1 and A2 are given as 10 centimeters. Okay, so the wheels are placed along the y-axis of the body frame and at an equal distance from the body frame. The distance between the two wheels along the y-axis is 40 centimeters, right? So the total distance between the two wheels is actually 40 centimeters. So basically, yeah, the distance d is nothing but 40. Yeah, then what will be the angular velocity? R of the robot with respect to the body frame of reference. So again, you know this relation UVR is given as that wheel configuration matrix. That is nothing but what was that again? Yeah, A by 2, 0, 0 minus A by 2D, A by 2D. This would be multiplied with omega 1, omega 2. Right? So like all the entries are basically given in the question. You are only required to substitute these values into this. Right? So if I substitute the values, I'll get it as A by 2 is 5, again A by 2 is 5. The second row is all zeros. And the third row is uh, minus A by 2D, that becomes minus 10 by 40. This becomes 10 by 40. And you multiply this with omega 1 and omega 2, that is 1.5 and 0.5. And if you multiply this out, you will get UVR. But you are only interested in the third, the third entry, basically. Right? You are only interested in the third entry. So you can consider, expanding this third entry. So you don't really have to bother about the first two entries. Right? And the third entry is minus 10 by 40 multiplied by 1 by 5, or minus 1 by 4 into 1.5 plus 1 by 4 into 0.5. So this would end up with, some entries at the first two elements, and the third element would be minus 0.25 radians per second. So in that case, the third column, third entry is nothing but the R, the angular velocity of the robot with respect to the body frame of reference. That is what it has been asked in the question. Right? So in that regard, our correct answer is option A. It's only a matter of substituting the parameters into the wheel configuration matrix. Moving on to question 3. If the number of controllable degree of freedom is equal to the total degree of freedom, then the system is called, right? What is the system called? Is it a mobile robot? Is it a holonomic robot? Is it a non-holonomic system? Is it a differential drive? Is it a structure? So if you can recall from the lectures, this is by definition, this is basically the definition of a holonomic system. right? So the thing is that if the number of controllable degree of freedom is equal to the total degree of freedom, then such configurations or such configuration of mobile robots can be classified as a holonomic system. I'll give you one example. What do you mean by this total degree of freedom? The total degree of freedom is, the number of coordinates or the number of independent parameters that you would need to fully describe, uh, that you would require to fully describe a rigid body, or in our case, a mobile robot, right? So for all the mobile robots, all the wheeled mobile robots, the total degree of freedom is going to be 3, right? Because if you consider this to be the frame of reference, inertial frame of reference, xi and yi, you require 3 coordinates to fully, to fully define the mobile robot base. So what are the 3 coordinates? You would require two position coordinates, to describe its position. So I'll call, this length as x and this length as y. You require 2 variables to define its position, and you require one more variable to define its orientation, right? I'll call this psi. So to locate a rigid body in plane, you essentially need 3 degrees of freedom. But then how many degrees of freedom can you control? That is the question, whether all the 3 degrees of freedom can be simultaneously controlled. If you can simultaneously control all the degrees of freedom, then such systems are called holonomic systems. And if you cannot control all the 3 degrees of freedom simultaneously, then such systems comes under non-holonomic systems. Like for example, in case of a differential drive robot like this, we have seen that, if I attach a frame of reference, if I attach this as xb and this as yb, we have seen that the differential wheel robot can go forward, it can go backward, it can rotate about its own axis with zero turning radius. It can, take a curve, in the clockwise or in the anti-clockwise sense or in the clockwise sense with finite turning radius, but it cannot move in the vertical direction. It cannot move in the lateral direction, right? Because these are conventional wheels and they provide infinite resistance along the lateral direction. And similarly, it cannot move diagonal like this. Whatever inputs you give to the 2 wheels, it cannot move in this diagonal sense. And as you can recall, from the wheel configuration matrix, this was a by 2, a by 2, 0, 0, minus a by 2d, a by 2d. As you can see, one of the row is fully 0. So that means it cannot have any velocities along the y direction or along the yb direction. So such systems, where it cannot have all the 3 degrees of freedom simultaneously, they come under non-holonomic systems. And similar in the case of a skid steering robot, a 4-wheel skid steering robot. So even though this has 4 wheels, it can only move similar to a differential wheel robot. It can rotate like this about its vertical axis with 0 turning radius. It can move forward, it can move backward. It can also take a curve trajectory with finite turning radius. But again, it cannot move in the lateral direction. Or it cannot also move in the diagonal direction. And as you can see, if you write the wheel configuration matrix for this uh, uh, skid steering robot, it'll also have the second row full of zeros. So such systems are non-holonomic. And another way of checking whether the system is holonomic or non-holonomic is that you take the rank of this W matrix, right? If you know the configuration, you should be able to know how to, assemble this W matrix. And if the rank of the W matrix is less than 3, such systems are non-holonomic. And if the rank is 3 or greater, such systems are holonomic. Right? So by definition, if the number of controllable degrees of freedom is equal to the total degrees of freedom, then such systems are called holonomic. If the controllable degrees of freedom is less than the total degrees of freedom, such systems are non-holonomic. So our answer is indeed holonomic because the statement is by definition is basically a definition of holonomic systems. Okay, so moving on to question 4. For a given mobile robot with 4 mechanism wheels, the wheel configuration matrix W is, given so and so. We have seen earlier in the slides how to derive this, but in the question they have already given the wheel configuration matrix. If the robot is to move in a lateral direction, then what will be the right combination of wheel angular velocities? It's the standard question that you can expect for your weekly assignments. So we know this relation, theta as W multiplied by W, where theta is nothing but UVR. And this W matrix is given as A by 4. So the entries are 1, 1, 1, 1, 1 minus 1, 1 minus 1, minus 1 by D minus L, minus 1 by D minus L, 1 by D minus L, 1 by D minus L. And this omega vector is the vector of angular velocities, omega 1, omega 2, omega 3, omega 4. And the question says, if the robot is to move in the lateral direction upward, then what will be the right combination of wheel angular velocities? You have to find out the right combination among the 6 options that you are given so that the robot will move in the lateral direction. So what does it mean by that? So if you consider this to be the robot chassis, with 4 mechanism wheels, we have seen that, the first wheel has passive rollers in this direction. Second wheels have passive rollers like so. Third wheel has passive rollers similar to the first wheel. And the fourth wheel has passive rollers similar to the first wheel. And you can also fix a body fixed frame of reference like so, XB and YB, right? And the velocity coordinates along XB is U. The velocity coordinates along YB is V. And the velocity coordinates, the angular velocity coordinate along ZB is R. So how do you interpret the question? In the question, it has been said that the robot moves in the lateral direction or in this direction. Upward in the sense it goes along the positive YB axis. So if the robot moves only in the lateral direction, that too along the positive Y axis, what information can you gain from it? Right? So lateral upward motion would imply that your theta vector would look something like this. 0, k, 0, where k is any arbitrary constant. Right? Because it won't have any component along the longitudinal direction. It won't have any component along the, it won't have any angular component. It strictly moves laterally, a pure lateral motion. So if that is the case, the zeta vector would look something like this, 0, k0. And from all the 6 options, you are required to find out the right combination so that if you multiply the wheel configuration matrix with the right combination of omega vector, you will end up with this, right? One thing is you can try each of these options one by one and see which of the combination would give, this vector. Or you can try the process of elimination. The first option is basically omega 1, omega 2, omega 3, omega 4, all are omegas. All are in the same direction and they have the same magnitudes. So like if all the wheels have same magnitudes and same direction, the mobile robot is going to be in the longitudinal direction, right? So we can eliminate this option. And what other options can you eliminate? What about the second option? Second option says wheel 1 goes in the negative direction, wheel 2 goes in the negative direction, uh, wheel 3 goes in the negative direction, and wheel 4 goes in the negative direction. All are equal magnitudes. So the mobile robot will go in the longitudinal direction, but in the negative sense, in the negative longitudinal direction. So we can also eliminate option 2. What about option 3? So option 3 is, omega 1 is plus omega, omega 2 is minus omega, omega 3 is plus omega, and omega 4 is minus omega, right? So these two diagonal wheels have equal magnitude and equal direction, and these two wheels have equal magnitude and equal direction. So we'll consider that, instead of that, we will substitute like, we will substitute here it is as omega, minus omega, omega, and minus omega. So if you multiply this out, what will you get? So the first entry would be plus omega, minus omega, plus omega, minus omega, it will be 0. The second entry would be omega, plus omega, plus omega, plus omega, it will be like 4 omega. And the third entry, this is minus 1 by d minus L. So this is minus and plus, that becomes minus. This is minus and minus, that becomes plus. This is plus and plus, that becomes plus. This is plus and minus. So this also becomes 0. It will add up to be 0. So as you can see, these are comparable, right? 4 omega can be considered as an arbitrary constant. So if you give this as a vector, if you give this as the control vector to the wheels, your robot will only, you will only have a V component. So in that regard, the robot can only move in the lateral direction. It does not have any component along longitudinal direction. It does not have any component along it does not have any angular velocity component. So in that regard, we can easily say that our option C is the right option. You can try other options if you want to convince yourself, but option 3 in this regard is the correct answer. So I hope that is clear enough. Okay, option 3 is indeed the correct answer. Now, moving on to question 5, it's a similar sort of a question. For a given mobile robot with 3 omni wheels, the wheel configuration matrix is given as so and so. Again, the wheel configuration matrix is given. Here also, if the robot is to move in a lateral direction upward, then what will be the right combination of these wheel angular velocities? Again, you are given the similar problem, zeta as W multiplied by omega, where zeta is UVR and omega is, W is given as 0 minus A root 3 by 3, A root 3 by 3, 2A by 3, minus A by 3, minus A by 3, A by 3L, This is A by 3L. This is A by 3L. And since this is an omni wheel, I hope you can recall what an omni wheel robot would look like. It has a circular platform with the body fixed frame attached like this, XB and YB. So it has three wheels which are oriented 120 degrees with respect to each other. So it has passive rollers like so. And the second wheel to be at 120 degrees like so. Again, you have the passive rollers. And the third wheel will be like so. You have the passive rollers like this. So since there are three wheels, you can have this omega 1, omega 2, omega 3. So here again, the requirement is that the robot has to move in the lateral direction, a pure lateral direction along YB axis. It should not have any longitudinal component, or it should not have any angular component. So our UVR vector should look something like this, 0, K0. And you are required to find out the right combination of the wheel angular velocity vector. So again, we'll do the process of elimination. So the first case is all the wheels have equal angular velocities. So it'll be like this, the first wheel has an angular velocity like this. The second one has an angular velocity like this. The third has an angular velocity like this. So if this is the command that you give, the robot would rotate about its own vertical axis, like so, a pure rotation. That is not what we wanted, so we can eliminate the first option. And the second option is, omega 1 is negative omega, omega 2 is also negative omega, omega 3 is also negative omega. So it also has a pure rotation, but in a different sense, in an opposite sense. So you can also eliminate that as well. What about the third option? Omega 1 is omega, omega 2 is minus omega by 2, omega 3 is minus omega by 2. Right? So you can try that. Instead of this, I'll substitute the third option, omega minus omega by 2, minus omega by 2. And if I multiply this out, what will you get? The first column, the first entry would be, 0 multiplied by omega. This is plus and this is a minus. So the first entry would turn out to be 0. And the second entry would turn out to be 2a omega by 3 plus a omega by 6 plus a omega by 6. So that becomes a positive quantity, I suppose, because, these minuses would get cancelled, these minuses would get cancelled. In the end, you will end up with a positive quantity. And the third element is actually, minus a by 3L multiplied by omega plus a by 3L multiplied by minus omega by 2 plus a by 3L multiplied by minus omega by 2. And if you expand this out, this is a omega by 3L minus this is plus a omega by 3L minus a omega by 6L minus a omega by 6L. So this entire term is actually going to be 0, right? So that term is actually 0. So again, we have obtained what we were actually looking for, because this is what we were looking for, or we should be looking for as per the question. And with this combination of wheel angular velocity vector, we obtained, this form. So our option is indeed option C. Once again, right? So that is indeed our answer. So yeah, moving on, question 6. For a land-based mobile robot, the wheel configuration matrix is given as uh, so and so. W is an M by N matrix where M is greater than N. Then what will be the pseudo inverse? And what is the pseudo inverse and what condition do we have to maintain for that? We can basically estimate the pseudo inverse. Right? So when M is greater than N, or when the W matrix is actually tall, right? When the number of rows is greater than the number of columns, it's basically an overspecified system. And like for an overspecified system, you cannot have an exact solution because it's an overdetermined solution. M greater than N means the system of linear equations is overdetermined, right? For example, if you have the theta as W multiplied by omega, where W is an M by N matrix. And if you want to find out omega, you have to take the pseudo inverse and pre-multiply it with theta. And basically, when the system is overdetermined, you will get this omega star, where this omega star is the least square approximation. Typically, we want theta minus W omega to be 0 because these are equivalent. But since we are only finding out an approximated value of omega star, this is not going to be equal. But omega star will ensure that the least square error between zeta and W omega star is going to be minimal. It's not 0, but there is a finite amount of least square error, but it's going to be very minimal. So in order to find out omega star, the pseudo inverse for overdetermined system, what we are looking for is the left pseudo inverse. Which is nothing but, by definition, it is nothing but W transpose W, the whole inverse W transpose. This is the left pseudo inverse. Right? And in order for this left pseudo inverse to exist, this regular inverse should exist, because W transpose W is going to be a square matrix. And in order for this inverse to exist, for a given matrix, by definition, inverse of a matrix is nothing but adjoint A by determinant of A. So in order for this determinant to exist, determinant of A should not be 0. It should be non-zero. Otherwise, determinant of A is 0, this inverse becomes undefined. So similar analogy can be brought here. In order for this inverse to exist, W transpose W, the determinant of W transpose W should not be 0. Right? And the condition for identity matrix is if you pre-multiply the wheel configuration matrix with its pseudo inverse, pre-multiply means you have to left multiply, you will get an identity matrix. Right? But in case of a regular matrix, the regular square matrix, A inverse A is I, or A inverse is also identity matrix. But in case of a left pseudo inverse, you can only left multiply with the actual matrix. Then only you will get identity matrix. W pseudo inverse may not be equal to I, right? So in that regard, the correct answer in this case, I believe, is option D, I suppose. Yes, that's option D, I think, is the correct answer. Okay, now moving on to question 7. You are given a matrix A as 0.1, 0.1, 0, 0, 0.5, and minus 0.5. This is an m by n matrix where m is 3 and n is 2. Number of rows is 3, number of columns is 2. This is just like the case that we have seen earlier. This is an over-specified or an over-determined system. And the pseudo-inverse, the appropriate pseudo-inverse of matrix A or P inverse is the left pseudo-inverse. And to figure out the left pseudo-inverse, the correct expression is a pseudo-inverse of A is A transpose A inverse A transpose. So if you do this operation with this matrix A, you would end up with the pseudo-inverse of A as you can do this on your own. I'll just give out the answer for this question. It's essentially, I believe it's option B, C, D, E, F. Should be option F. Sorry, it should be option D, I think. A, B, C, D. Unless I am very much mistaken. 501. Sorry, it's option A, actually. Right? So if you do this, you have been given A, and if you do this, A transpose A, and whatever you get, you take the inverse, and you post multiply that with A transpose, you will get this as your answer. 501, 50 minus 1. Right? So it's a numerical exercise. You can work it on your own. Okay, and moving on to question 8. What do we have over here? A mobile robot with 3 omni wheels. The wheel configuration matrix is given as so and so. If the wheel angular velocities are given as so and so, then how will the mobile robot move? Right? So it's the inverse of the problem that we have seen earlier. Right? So you are given the wheel configuration matrix as so, W as 0 minus A root 3 by 3, A root 3 by 3, then 2A by 3 minus A by 3 minus A by 3. Then you have A by 3L, A by 3L, A by 3L. And you have been given the angular velocity vector as omega minus root 3 omega by 2 minus omega by 2, then root 3 omega by 2 minus omega by 2. So if you multiply this out, you will get this zeta vector. And based on the structure of the zeta vector, you can determine how the robot is going to move. Right? And for that, you have to, expand this matrix. You have to evaluate that matrix. So I'll do that quickly. So the first entry would be 0 plus 3A omega by 2 plus A root 3 omega by 2 minus A root 3, minus 3a omega by 2 minus a root 3 omega by 6. Unless I am very much mistaken, I think this term is 6. All the terms are 6 actually, because yeah, there's a 3 and a 2 over here, so that becomes a 6. The third entry, one second. Did I do this correctly? This is a positive quantity. This is a positive quantity. And this is a positive quantity. And this is a negative quantity, I guess. So these two terms will get cancelled. Plus, yeah. And what about the second row? You get 2a omega by 3 plus a root 3 omega by 6 plus a omega by 6. Then you have minus a root 3 omega by 6 plus a omega by 6. I believe I am correct. So in this case also, these two entries will get cancelled. And the final entry would be a omega by 3L. Then you have minus a root 3 omega by 6L. Then you have minus a omega by 6L. Then plus a root 3 omega by 6L minus a omega by 6L. So here again these two terms will get cancelled. So if you expand this out, you will get the first entry would be 3a omega by 6 plus 3 omega by 6, that is a omega. And the second entry would be 2a omega by 3 plus a omega by 6 plus a omega by 6. So that also makes it a omega, basically, right? That is also a omega. And the third entry would be a by 3 minus a by 6 minus a by 6. That is 0, actually. So this is how your zeta vector would look like. This is u, this is v, this is r. This is your zeta vector. So what can you infer from this? It has a u velocity a omega. It has a v velocity a omega, but it has a 0 angular velocity. So in that regard, the robot, your omni-wheel robot, which is something like this, with 3 omni-wheels like so, and if you consider this to be xb, and if you consider this to be yb, it has a velocity in the u direction, it has a velocity in the v direction. Both are of equal magnitude and both have the same sign. So that makes the robot's trajectory to be, in a diagonal way. Equal velocity along xb and equal velocity along yb, so that the robot will move in the diagonal, in a diagonal way with equal velocities. So what is the correct option? What is the most applicable option? It will go forward along positive x-axis, that is false. It will go along the forward. The first two options are obviously false. Third option is it will move diagonally along the first quadrant. with equal linear velocities in both axes, keeping the orientation constant. So that is actually true, right? So based on what we have seen from the structure of the zeta vector, it will have equal uh, linear velocities along xb and yb axes. It has zero rotational component, so it will move in the first quadrant diagonally with zero angular velocity, or it will move with constant orientation. So in that regard, option C is the correct answer. Okay, so moving on to question 9. For a robotic system with more number of system states than controllable inputs, which of the three statements are true? An exact solution for controllable inputs of vector of systems can be obtained by W as omega as W inverse zeta. So you know this relation zeta as W multiplied by omega, and it is given that the number of system states zeta is greater than omega. The number of elements in zeta is greater than omega. So our m by n W matrix would be a tall matrix, right? Where m is greater than n. So when m is greater than n, obviously you cannot take the pseudo inverse. Well, you cannot take the regular inverse, because it's not a square matrix. So option the statement 1 is actually false. And what about statement 2? An approximate solution can be obtained by finding omega star such that it minimizes the least square error zeta minus W omega. So that is actually true, right? Because when a system is overdetermined, you cannot find an exact value for omega. You can only find an approximate omega star, which basically minimizes the error between zeta and W omega star. Ideally, we want this to be equal, but we can only find an approximate omega star where the least square error is minimal. So that option is indeed true. And the third is the analytical solution for the above least squares problem is given as so. And if you can recall, this is actually the right pseudo inverse. This term is the right pseudo inverse, which is obviously not applicable for an overdetermined system. For an overdetermined system, in brackets m greater than n, we use the left pseudo inverse. So that makes option 3 as also false. So the only correct statement is option 2. So in that regard, our correct answer is only option 2, or statement 2. So that's indeed the correct answer. Moving on to question 10. The wheel configuration matrix for a 4-wheel skid steering robot is given as so and so. And if the wheel velocities are given as omega 1 is 4 omega, omega 2 is 3 omega, omega 3 is 2 omega, and omega 4 is omega, what is the instantaneous lateral velocity along the y-axis of the robot with respect to the inertial frame of reference? So consider at this instant the x-axis of the body frame is oriented 90 degrees with respect to the x-axis of the inertial frame. Right? So this is similar to all the problems that we have seen. We have this relation zeta as W times omega, where W is given as a by 4, a by 4, a by 4, a by 4, 0, 0, 0, 0, minus a by 4d, minus a by 4d, a by 4d, and a by 4d. And you are also given the omega vector as 4 omega, 3 omega, 2 omega, and omega. And if you multiply this out, you will get the theta vector as UVR. Right? So if you multiply this out, what will you get? It'll be basically a by 4 multiplied by 4 omega plus 3 omega plus 2 omega plus omega. Then the second entry is obviously going to be 0. And the third entry is minus a by 4d multiplied by 4 omega plus 3 omega. Then you will have minus 2 omega minus omega. And if you expand it out, you will get a by 4 multiplied by 10 omega, 0. Then minus a by 4 b multiplied by 4 omega. This is your UVR. But in the question, it says you have to find the lateral velocity, in the y-axis with respect to the inertial frame of reference. So far, what we have obtained is with respect to the body frame of reference. And from the first week, if you can recall, the mapping between the inertial frame of reference and the body frame of reference is through this mapping. Eta dot is a Jacobian matrix multiplied by the theta vector, where eta dot is x dot, y dot, r dot. And the Jacobian matrix is can be computed by cos 90 because both of the frames, the body fixed frame and the inertial frame are oriented 90 degrees with respect to each other. So this is cos 90 minus sin 90, 0, sin 90, cos 90, 0, and this is 0, 0, 1. And you multiply this out with the value that you got over here. So I'll write it as 5a omega by 2. Then the second entry is 0, and the 4 is minus a omega by d. I'll just keep this away. Sorry. Right. So if you substitute the numerical values for cos 90, it's going to be 0. Sin 90 is minus 1. Sin 90 is 1. And cos 90 is 0. So if you multiply this out, you will get, I think you are only interested to find out the y dot. All right. So if you consider the second row, y dot is nothing but 5a by 2, 5a omega by 2. That is your answer. So I guess it's option B for question 9. Sorry, question 10. Yes, question 10. Okay, so 2 more questions. Sorry, 3 more questions. For a robotic system with more controllable inputs than the system states. So we have this general relation, wheel matrix relation, zeta as W multiplied by omega. So more control inputs means m is less than n. So the W, the wheel configuration matrix, would be a very short and broad, matrix. So if the number of controllable inputs is more than the number of system states, then that essentially makes this system an underdetermined system, right? Underdetermined. So like from linear algebra, you know that if the system is underdetermined, you can have infinite number of solutions, infinite number of solutions. And, from this infinite number of feasible solutions, you select the solution that has the minimal norm, right? Minimum norm or the norm of the omega vector is minimal, but subjected to these constraints. You have to find out an omega with a minimal norm, but you also have to make sure that zeta minus w omega is zero, right? It cannot be any omega vector. You have to find out an omega vector such that zeta minus w omega is zero. And out of all the solutions, why are you selecting a norm, or why are you selecting a solution with minimal norm? The reason is that, this term, the square of the norm or this omega square usually corresponds to the energy of an actuator or energy of the vector of actuators, right? As you know, kinetic energy is proportional to the velocity square. So by choosing the minimal norm solution, in effect, you are choosing a solution that has the least amount of energy. I hope that makes some sort of sense, you know, so that the norm of all the motors or all the actuators of a mobile robot would be minimal compared to any other feasible solution, right? Those could still be feasible, those could still satisfy this constraint, but the norm of this omega vector would be very high, or in effect, the energy spent for realizing that solution would be very high. So minimal norm, you can consider it to be, an analog, or it could be analogous to the minimal energy spent. So that's why we are very interested with minimal norm, minimal norm solution. So yeah, what are the correct statements? For a given system state, multiple control inputs can be possible. That is indeed true, for an underdetermined system. The control input with minimal norm is found by minimizing the objective function. Minimize the norm subjected to the constraints. Zeta minus w omega should be zero. That is also true. And the exact solution for this above optimization procedure is given by this one. But I hope you can see this enough that, this expression, W transpose W, the whole inverse W transpose is the pseudo inverse, is the left pseudo inverse, right? And for underdetermined system, we go for the right pseudo inverse. Because if you want to know about the derivation, or if you want to know the reasoning behind that, you can refer back to the lectures of Professor Shantakumar. Or if you have any more doubts, you can raise that in the discussion forum. Maybe a TA would probably answer that. But for the time being, the correct answer for this is that the pseudo inverse for an underdetermined system has to be the right pseudo inverse. And the expression for right pseudo inverse is W uh, W transpose the whole inverse W transpose. This is the right pseudo inverse for underdetermined system. So option 1 and option 2 statements 1 and 2 are true, but statement 3 is actually false. So in that regard, our correct option is option B. Okay. So yeah, that's about it. The second last question, pick the odd one from the following mobile robot base configurations. So out of these four, which of them is the odd one out? Is it the differential wheel drive? Is it the 3 omni wheel drive? Is it the mechanism wheel, or is it swerve drive? Because if you can recall the definition of holonomic and non-holonomic robots, the last three are basically holonomic robots, holonomic mobile robots. Because if you evaluate the rank of the wheel configuration matrix, it'll be at least it'll at least be equal to 3. Or in essence, they can move in any sort of direction. If you consider this to be the chassis, it can move forward, it can move backward, it can rotate about its vertical axis. It can take a trajectory like this, with finite turning radius. It can move in the lateral direction. It can move diagonal. All sort of ways it's possible for the last three options. But in case of a differential wheeled robot, it's not a holonomic robot. It cannot move in the lateral direction, and it cannot also execute a diagonal path or a diagonal trajectory. Right? This is not holonomic. So in that regard, the correct answer is option A, because everything else is holonomic and differential drive is not holonomic. So that is option A. And the final question for this session, pick the odd one from the following mobile robot configurations. Again, it's an odd one out. So we have a differential drive. This is non-holonomic. And 4-wheel skid steering. Again, that is also not holonomic. It's similar to skid steering. The capability is still similar to skid steering, but it has 4 wheels, 4 powered non-steerable wheels. Omni wheel is holonomic. And tricycle like, 1 powered plus steerable wheel plus 2 non-powered passive wheels at the rear axle. So it's like an auto rickshaw, right? You have a chassis like this. You have a powered and a steerable wheel at the front. It is powered, it is also steerable, but you have, 2 passive wheels, not driven wheels at the back. So a tricycle is also non-holonomic, right? Because you will never see an auto rickshaw going sideways like this. It cannot simply go sideways like that. It can only go like, it can only go like this. It can only take a finite turning radius. It can also, it cannot also rotate about its vertical axis. And what about a bicycle-like configuration? So in the bicycle-like configuration, we have a powered rear wheel and a steerable front wheel in case of a bicycle. Again, as in case of a bicycle, it can move forward, it can go backward, it can take a curve, but it cannot go in a lateral direction. It cannot also move diagonally, right? Like this. It cannot keep its orientation and move diagonally. So a bicycle-like configuration is also non-holonomic. So in that regard, the odd one out is, the 3-wheel omni-wheel drive, because everything else is non-holonomic. The 3-wheel omni drive is only holonomic. So in that regard, option 3 or option C is indeed the correct answer, right? Yeah, so with that, we'll wind up today's session. I hope it has been useful. I'm sorry that it has exceeded the allotted time. I know we have covered a lot of topics, a lot of questions and a lot of topics covered. Thank you for bearing with me. If you would like to revisit whatever we have discussed, the recording of this video would be updated in YouTube, probably by tomorrow. if you want to, revisit some of the things that we have discussed, feel free to, you know, revisit back. So until then, yeah, someone has said, yeah, I can share the slides. I can actually share these slides. It'll be uploaded. Yeah. So again, thank you all for attending. We'll continue our discussion next week. Next week we'll talk about dynamics, right? I'll try to restrict the session in 2 hours as well. Okay, so until next week, thank you for attending. You can all log off. See you next week. Bye. Thank you.